This presentation is about acoustic fundamentals. It's the first part of a two-part series where the second one is about building acoustics. So you can take those fundamental information and apply it to your building projects, especially for architects and for external noise is a lot of what the second part will be about. So this presentation includes the physics of sound, understanding decibels, understanding psychoacoustics, understanding acoustic scales, and understanding the difference between sound power and sound pressure, which are really important for us, especially those of us in the HVAC industry. So I'm going to be the main presenter today, Jeff Bolt, fellow at ASHRAE, and a bunch of other stuff you don't care about. But I do have nearly a master's degree in acoustical engineering, so I know what I'm doing, I think, pretty well. And I rewrote the ASHRAE chapter about acoustics in the duct design guide. So I spent 2 years of graduate study at Heriot-Watt University in acoustics, vibration, and noise control, emphasizing building systems and noise control. And I've read a whole lot of acoustical books, so that's kind of my background in acoustics. So, also, we don't have them speaking today, at least Dave Wright will not be speaking, but when you have acoustical questions, I would really like in IMAG that your acoustical questions come to David Wright and to Matt Boris, because I do a whole lot of things other than acoustics, and they specialize in acoustics. So they should really be the people you're bringing business to. So talking about physics of sound. So sound is a compression. If you're an old person like me and you grew up with a slinky, it's a lot like pushing on the end of a slinky and then pulling it back. It's a compression and rarefaction wave. We often draw it as a sine wave, but that's not quite exactly the way it works. But from a mathematical standpoint, it works fine that way. But the molecules are getting pushed tighter together and then spreading wider apart. So the speed of acoustics in air is about 1,100 feet per second, or about 750 miles per hour. That's why if you're on a commercial airplane that goes above 750 miles per hour, it falls to the ground and you die. The exact speed of sound depends on the material it's in. Mostly it's determined by density. For example, it's much faster in metals than it is in air. It also depends somewhat on temperature. So it's faster at high air temperatures or high water temperatures, for example. And the basic equation is velocity is equal to force times wavelength. So in terms of the audible range for the human ear, a young, healthy person can hear from about 16 hertz to about 20,000 hertz. And if you ever bought a stereo, they usually say 20 to 20,000 hertz, it has such and such performance. That's the range for a young, healthy person. For a person my age, you probably can't hear past about 13 or 14,000 hertz on the high end. I don't think it drops off nearly as much on the low end. So, but that means the wavelengths of sound vary from 68 feet for the lowest sounds you can hear to about 5/8 of an inch for the highest sounds you could hear if you were young. And you hadn't listened to too much rock music. Just to give you a reference, 1,000 hertz, which is kind of the center of our hearing spectrum, the sound length, the wavelengths are about 1.1 foot. So you can think of 1,000 hertz as 1 foot, and that'll give you a good reference for doing quick in your head math. So human speech varies only between 500 and 5,000 hertz. So it doesn't have any really low frequencies. I mean, unless you're James Earl Jones. And it doesn't have any really high frequencies, at least not super high frequencies, which is why you used to be able to get a 1970s Bell telephone that had a really crappy microphone and a really crappy speaker, and it worked fine for human speech, but it wasn't so great for music. So if you're a musical person, which I'm not, middle C is 262 hertz. So a little lower than the 1K that we think of as a reference. And a grand piano will go from 28 to 4,200 hertz approximately. So when you send somebody out to a project site and they come back and they give you their impression of the noise, this is a chart that I sort of stole from ASHRAE. And it tells you what words they will give you to tell you what frequency the sound is in. And it was a statistical survey of, I think, quite a large number of people. So, you know, throb or rumble or roar or hiss. When you hear the word hiss, you know it's diffuser or a volume damper noise. When you hear that noise, the word rumble, you're thinking this is probably going to be either coming from the main fan or coming back to a refrigerant compressor. Okay, so the human ear is an amazing instrument. It hears over a range of 140 decibels before you die. So 140 decibels is 10 with 14 zeros behind it. So it's 100 trillion to 1. And the accuracy is about plus or 5 dB, which is pretty good. So it would be a lot like if your boss told you, I want you to go back to your cubicle and build me a scale or design me a scale that can weigh small ants, and it can weigh the largest aircraft carrier, which is the USS Gerald Ford, and with decent accuracy. And and that's when you go back to your cubicle and you just start crying if you're an engineer, because you don't know how to do it.
Hey, Jeff, if I could jump in real quick. This is Matt Boris, everybody. If you can go back 2 slides to the names or how we describe the noise. This is one of the most helpful kind of descriptions of noise that you can give to the acoustical team if you've got a mechanical noise problem. Because each of these frequency bands really changes the options we have for treatment. So if you come back and say, oh, we've got a hiss, then we know we've got options, whether it's duct lining, absorption, silencers, whereas rumble is much more like it says poor vibration isolation. So if you can kind of get this in your head, it really gives us a good characteristic of what the problem is and how we should go about treating it. So I just wanted to make that point real quick.
Yeah, thank you, Matt, because we actually had a project yesterday where somebody had been out to a job site and the acoustic meter failed. And all we really had was his verbal description of what the sound was like. And that helped quite a bit. Okay, so when sound bounces off a surface, it can bounce off in 2 different ways. It can bounce off specularly, which is like a mirror, or it can bounce off in a very diffuse manner, and it depends on the ratio of the length of the sound wave to the size of the surface. So very high frequency sounds are much more likely to bounce off in a diffuse way, and very low frequency sounds are much more likely to bounce off in a specular way. And if you got a mirror at your house, you know that it's typically silvered behind it, and it may rust out from the edges, but in the most of the mirror, it'll bounce off in a specular fashion. So when you're trying to dissipate noise or reduce noise, there are a couple different ways, well, three different ways. One is dissipative absorption, which is the most common. So this is friction that converts noise to heat. Noise numbers are typically very small in terms of the amount of power there is in them and the amount of watts that are in them. So it doesn't take a lot of friction to absorb the noise. But when you've got something like a fiberglass or a rock wool absorber, what's actually happening is the acoustics moves the fibers and they rub together and they create friction and they turn into heat. And it's really small amounts of heat, so don't count on heating your house that way. Although there are acoustic refrigerators now that I think Jerry and Tom's are using. But in general, the absorber that you need to reduce sound effectively should be at least a quarter of a wavelength thick, at least if it's put on a wall or a ceiling. If it's in mid-air, it's not such a big deal. But if you're putting acoustical absorbers on a wall, it should be at least a quarter of a wavelength thick. So, also the materials that absorb acoustics really well, a lot of them are fibrous, or they might be expanded foam, and they may need coverings. For example, if you're in a hospital, they need to be cleaned. They need some durability. They might need a vapor barrier. So, there are other things to be thought of there. On the far right lower corner, I've got an example of 4 different sound absorbers. And I did an analysis of which ones work best. And in my opinion, option C works best. And that's what I designed for one of our clients. And I think that pretty much matches what you'll get from the really big, well-tuned in sound absorber manufacturers like Vibroacoustics or someone like that. So another option you have is reactive absorption. So this deals with tuned frequencies, and it's typically very narrow band if there isn't dampening added to it. It's much best for narrow frequencies. You see it a lot in vehicle mufflers. If you've ever had a car muffler and somebody said, well, I was going to get a different style that uses a packed muffler, that will get you better performance, but it will have fiberglass or rock wool in it, and it may quit after a year or so. But when you look at absorptives, a reactive silencer, and you typically see them in fume exhaust systems where they can't have fiberglass or rock wool in them because they would absorb the chemicals, they will have very much smaller holes. So if you see little tiny holes like you see in this picture, that's a reactive absorber. If you see bigger holes, like a 1/4 inch, that's a typical absorber. Reactive absorbers cannot equal the performance of our typical absorbers, but they have advantages because they don't have any packing in them, so they won't absorb chemicals or anything of that sort. One interesting example of an absorptive, or excuse me, a reactive silencer is gypsum board on 16 to 24-inch centers is a very good reactive absorber of transformer noise, because transformers generate 60 hertz electricity in the United States, and their peak frequency is twice that, so 120 hertz. And at that frequency, gypsum board is actually a very good reactive silencer for that noise. So, I was talking a little, I jumped ahead of myself, but you see mufflers come in packed and dissipative type. One performs better, the other lasts longer. So the third method of reducing noise is active noise silencing. What the idea is you measure the noise and you send out an exactly opposite frequency to cancel it out. The issue is it has to be a controlled situation. I think Digisonics was the last manufacturer that I know of who is doing it in duct systems. It works better at low frequencies. In the old days, it was hard to do because we didn't have computers that were fast enough to do the fast Fourier transformation and cancel the noise. Today, I don't think that's the issue. I think the issue is the noise has to be pointed in the same direction. And down a ductwork with liner in it, I think that's pretty easy to do. Down a normal duct or in an exhaust stack, it can be tough. And there are temperature limitations too. I tried to do one on a 2,000-degree exhaust stack from a natural gas power generation unit, and they said they didn't have speakers that could handle that kind of temperature. But maybe some companies will get back into that business and will have some ability to do that. So now I'm going to talk about decibels, because math got tough when decibels were decided upon. Alexander Graham invented the bell. So, Alexander Graham Bell, the bell, that makes sense. And he wanted it to be used to handle large ranges of acoustical volume. And a decibel is a ratio. It's not a quantity. So later, people decided that the bell often had numbers less than 1, and they didn't like that. So they invented the decibel, which multiplies it by 10, which made all our math harder. Although nowadays with spreadsheets, it's not that hard. So I also want our engineers to understand the difference between sound power and sound pressure, because that's really critical to specifying equipment. When you see something that says LW, the way I do that in my mind is I go, W is watts, that's power. And sound power is the amount of sound energy coming out of that piece of equipment. And if you're a lighting person, it's a lot like lumens, the total amount of light coming out of your light fixture. Whereas sound pressure, which is often abbreviated LP or SPL, is the amount of pressure that's hitting your ear when you're listening to a sound. And that's, if you're a lighting person, it's like foot candles. And they're very different. And we often get information from manufacturers that doesn't say which one it is. Or if it's sound pressure, it really needs to say how far away from the piece of equipment it is. Otherwise, it's just useless information. So for a young person at 1 kilohertz, kind of near the middle of our ear's hearing range, 0 decibels is the minimum audible level. At 1 kilohertz, 120 decibels will be painful to you. So a little bit more about doing decibel math, because if you want to do it in your head, it's really not all that hard. If a sound has 1 decibel and you double the amount of sound power or pressure, because they're both ratios, that's going to add 3 decibels. So it's like if I've got 2 diffusers at the same sound power coming out of them level, at my ear, it's going to be 3 decibels louder. If I've got 4 diffusers, it'll be 6 decibels. So you can think of, if I double the number of items, it's going to add 3 decibels. If I quadruple it, it'll add 6 decibels. If I put in 10 times as many diffusers, and they'd have to be the same distance from your head, it'll add 10 decibels. And it keeps going up that way. So if you have 100 times the energy, so that's 2 zeros, that's 20 decibels added. So adding each 10 decibels adds a 0. And my wife sometimes tells me that everything I ever learned was from Star Trek or Jethro Bodine from the Clampetts TV show. And he said, you know, them zeros, they ain't nothing, but yet you adds them up and they's powerful. And that's the way decibels work. So if you want to add decibels, and I'm not going to spend much time on this, but divide each number by 10, take the anti-log of each number, add the numbers, take the 10 times the log of the sum, multiply by 10. We've got a spreadsheet that does this. You don't need to worry about it. An idea about sound pressure, you know, varying from different things. So a Saturn rocket, 194 dBA. I'm assuming this is near the rocket. That would pretty much blow your eardrums out and maybe blow your head apart. You know, ramjet at 160, that would be really harmful to you. Propeller aircraft at 140, that wouldn't be good for your long-term hearing. So, you know, and going down to quiet residential places, where in DBA, a private office, I would normally expect somewhere around 40 dBA. And you know, if you come into the office really early in the morning, you may notice that you can hear people all the way across the room, because if the room is quiet, your ears are really sensitive. So I'm going to talk a little bit about psychoacoustics. So an octave is doubling the frequency. So 20 hertz to 40 hertz to 80 hertz, etc. In the HVAC industry, the octaves that are normally listed for your equipment are the 63 hertz up to 8,000 hertz frequencies. Normally, equipment is not rated at 31.5 hertz, and it's normally not rated at 16 kilohertz. There are some codes that require that, but it's not normal you're going to be able to get a rating from an equipment manufacturer. And it's because it's really hard to build an acoustic chamber that can deal with 31.5 hertz, because you need sound absorption panels that are many feet thick. I've been down to Greenheck's facility, and they have two really good, an anechoic and a reverberant chamber, but they really can't handle 31.5 hertz either. So in terms of psychoacoustics, which is how acoustics reacts with a person's brain, hyperacusis is a poor ability to accommodate a big difference between volume ranges. It's most common with elderly people and with young people. I can remember my grandparents leaving a theater because it was a sci-fi movie and it was just too loud. And also, your children may run around and go kind of crazy when the vacuum cleaner is on because at those ages, they generally have trouble dealing with big ranges of volume. So another item about hyperacousis is your sense of direction, like where the sound is coming from, is mostly from phase effects. And by that, I mean the sound hits my left ear before my right ear. And if it hits my left ear before my right ear, I turn to the left because I know that sound is coming from that direction. A little bit, it's also from shadowing, like my head blocks part of that sound, and it's not quite as loud in my right ear. And this becomes important in some places. I'm thinking of an old movie that I watched where there was a cougar or a mountain lion up in a tree and was growling, and the deer kind of looks around and doesn't know where it's coming from because from that direction there was neither a phase effect nor a shadowing. And it comes into concert hall design. Like a lot of concert halls are designed in a fan shape, and that gets the most people the closest to the band, but it doesn't produce the best music. Boston Symphony Hall is probably a good example of a room that is rectangular. And so it has bounces off the walls coming to your ears, and you can actually look to see where the violinist is. Whereas in a fan shaped theater, you can't find that information quite so easily. It's also vertical symmetry. When you look at a Dolby sound system, it comes from different directions, and it is counting on your ears knowing which direction it comes from. So if you're laying on the couch, the Dolby doesn't work because you can't tell what direction the sound is coming from because your ears are in the wrong plane. So hearing loss can come from two different paths. It can be a conductivity issue, which is a mechanical failure of your ear. And today, our medical science can repair every single one of those. It can also come from sensory neuro, which is your ear sending an electrical transmission to your brain. And just backing up a little bit, an example of conductivity failure is like a puncture of your eardrum or the bones calcifying and it doesn't transfer it right. Sensory neuro is by far the most common, and it's also irreparable, which, in my opinion, demonstrates the complete superiority of mechanical engineers over electrical engineers because we can fix all of them. So hearing loss varies between the sexes. Here's a graph of hearing loss for women over time. And the next slide is hearing loss for men. So men lose, I'm going to back up a little bit here and show you the other one again. Men lose a whole lot more hearing loss at high frequencies than women do. And I do not know if this is skewed, because of the era when it was created in. But I think it's still a fact today. And when you look at a noisy environment, so most of the information in human speech is in the consonants. It's the t, sh, k, where most of the information is. The vowels add volume, but mostly the consonants give you information. And the consonants are all the high frequencies. So when my wife says I didn't listen to her, I usually say, honey, I can hear you, but all I get is wah, 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 because I can't hear the high frequencies anymore. So for all the men listening, that's the best I can give you for an excuse for not listening to your spouse. Okay, acoustic scales. There are a lot of them. And Leo Baranek created the most of anybody. So fons are curves of equal loudness. And these were mostly tests done on military age college men to develop those curves. And the idea is to come up with a single number that's at 1K, the perceived loudness. And it uses the decibel scale. So here's a picture of the fon curves. And notice, and in this curve, or this graph, the lowest volume levels are at the bottom of the graph. And the really high volume levels at your Who concert are at the top of the graph. But notice that at the bottom of the graph, there's a much deeper belly to that curve. And that's why there are several different curves. I think I'll get to it in a slide, but it's much flatter at the high frequencies. At the high volumes. At high volumes, your ear is a much more linear transducer than it is at low volumes. Most people would consider an increase of 10 decibels double the volume, from a survey of people doing tests. One zone is 40 fons, 2 zones is 50 fons, etc. If I've got a bathroom exhauster in my bathroom, I'm not accepting anything above 1 zone and probably not above a half a zone. Because I think it's too loud. I don't think in our company we should use zones for determining the level of things like grease exhausters, because I think dB or dBA or sound power are much better measures. So if you're doing noise masking, you may have heard of pink noise and you may have heard of white noise. And pink noise has equal power per octave. So that's my purple curve there, trying to be close to pink. White noise has equal power per hertz and is very different. And in general, pink noise does a better job of sound masking than white noise does. Okay, so our weighting scales. dBA is by far the most common one number value. It resembles the 40 fon curve from a couple slides ago. OSHA uses dBA. I have no idea why they use dBA, because it was designed for low noise levels and OSHA is regulating high noise levels, but that's what the rule is. dBB was developed for louder sounds and resembles the 80 fon contour curve. Nobody ever uses it, so you can forget about it. dBC is for even louder sounds. And if you have a cheap noise meter, the dBC curve will just be the unweighted curve where it doesn't do anything to it. Like I bought a Radio Shack meter years ago, and dBC and flat scale were exactly the same thing. But normally what happens on an old-fashioned, inexpensive sound meter is they have electronic resistors that adjust the noise in each band and then push them back together again. And they do pretty well. So flat weighting is my red line here. It weights all frequencies equally. You can see DBC weights it slightly, but you can see, look at DBA. Look at the huge weighting of that. At low frequencies, it can cut it down by over 50 decibels. So they're very different, and it's really important when our people go out and take sound readings, that they understand the difference and record what their meter is doing and which scale it's on. So here's an upside down version of the dBA curve. And this one only goes down to 63 hertz. And it gets much steeper as you go to the left. But our ear is the most sensitive at about 2000 hertz. I personally think cell phone apps work quite well for doing acoustical measurements. I usually use the RTA app. I mean, this is 2019. There may be better ones coming up. But I tested my phone, and it was within 1 decibel of the readings that we were getting from a multi-$1,000 laboratory instrument at Greenhex Factory. So I think they can work pretty well for most of the stuff we do, if our people have a good app. I am a little upset with Apple because they changed the carrier frequency of their phones, and now the octave bands don't show up quite right, but they still come up with accurate readings in my estimation. So other noise criteria. Beranek has proposed several number criteria. NC is one of them. And NC, when you specify a diffuser or a VAV box, they're rated in NC. And NC is not a noise level. It's an annoyance level. And it's based on the worst octave band that you have coming out of it. So you could be really, really quiet in 7 octave bands and be loud in 1, and you'll get a crappy NC rating because it will annoy people. And it emphasizes the high frequencies because those annoy people most. And it's used by AMCA for ratings of grills, registers, and diffusers. AHRI uses it for VAV boxes. But looking at the curves, the worst spot your noise touches on any one of those curves determines the NC level. So then Beranek came up with preferred noise criteria. And these are better than the NC criteria, but I don't think anybody uses them. And then came NCB, which was another improvement, but also never used. But the spreadsheet I developed will calculate all of those. So then came room criteria, which ASHRAE developed. It's not as common as dBA or NC, but it does give you more information. It'll tell you a little bit about the character of the sound. So if you see an RC35 with an R after it, that means there's a rumbly sound, so low frequency. And if you see an RC35H, it means it's got a hissy sound. I personally like that method, although I think ASHRAE's TC 2.6 thinks it's more of a figure out my problem thing than a specification of new products thing. So here you see the RC curves. They're pretty simple. They're straight lines. And then in the upper left, you see the I've got a lot of rumble, and you see I've got my building shakes. is what the two dotted areas in the upper left are. So RC Mark II is the latest ASHRAE index. It's an improvement on RC, but it's also a little bit more complex. Has pretty strict criteria for a normal frequency distribution, but I think it's very useful information for us getting our designs correct. So there are a few different ways to calculate noise levels. A lot of our people use an app from Vibroacoustics or just have Vibroacoustics do the calculations. And I think that's a perfectly good method because their policy is that if they're put number one on the schedule, that they'll guarantee the performance of the silencer. Also, we have the spreadsheet that I developed, which will do almost anything if you can figure out how the mind of Jeff Bolt works and work through the spreadsheet. But it will calculate unweighted dB, dB8, NC, Mark II, outdoor property noise. That's actually the fastest of all the acoustical calculations to make in the world, is doing outdoor property noise calculations. So here's an example of an output from a room noise criteria in a building. And you can see it comes up with dBA, it comes up with RC Mark II, it comes up with NC. So it pretty much comes up with everything. Okay, so outdoor noise. I'm trying to go fast here because I know I'm running late on time. So temperature makes a difference. So we don't do a lot of this, but if you're working at a facility that does blasting for like granite mining or something like that, they care about temperature inversion because normally temperature inversion drives the sound upward, but sometimes it drives it downward. And there are cases where they cannot blast because they're near a city and the temperature inversion will drive it down to them. And you can see I say make a better graphic. So I've got to work on this one. But also it's used for measuring global temperature. In the ocean, for example, the coldest part of the ocean is not the top and it's not the bottom, it's the middle. And they will send sound signals from Australia to Hawaii. And from the time it takes them to reach, because sound travels faster in hotter conditions, they can measure whether global ocean temperatures are going up. That's also why a lot of people think whales can communicate along wide distances, because their sound spreads out in 2D like a pancake instead of in 1D. Okay, so I did this slide kind of backwards, but when you have a normal device that's in free space, and by free space, I mean hanging from a crane, it has uniform spherical radiation, and the Q factor is 1 because nothing is reflecting the noise. If you have and I'm moving to the center now, uniform hemispherical radiation, which is the most normal for us, like air-cooled condensing units sitting on a concrete pad, it spreads out in hemispherical radiation. And so all the noise that hit the concrete pad bounces back up into the air. So you add 3 decibels to the noise level from it. And, you know, if you back it up against a building, then you get more restricted radiation, and you get an adder of 6 decibels. And it keeps going. If you put another wall against it, you're at 9 decibels. If you put a roof above it, you're at 12 decibels. Eventually, you're at a megaphone. So putting barricades around a loud piece of equipment. Like let's say we've got a air-cooled chiller or air-cooled condensing unit outside. When you put a wall around it, it does have a shadowing effect, especially at high frequency. So, and when you calculate that, the noise, the amount of noise you reduce it by depends on the extra distance going over the wall versus going through the wall. And it's a relatively long equation, but it's really simple in the spreadsheet that we have. And this is an example of a service we offer. This is an acoustical generator, natural gas powered. I think this one was maybe about 4 megawatts. And it has a noise level so low that it meets Illinois Title 35 compliance, because that picket fence is the fence of the mother of an attorney who understood Illinois Title 35 and how super restrictive it was. And this thing passed with no problems. In fact, we had to have people turn off their cars idling 50 yards away because we couldn't measure any noise from it. So it is a service that IMEG offers, is designing really high attenuation emergency generator enclosures. Okay, just one note. When people tell you, oh, there's going to be foliage and grass and stuff like that, and it's going to attenuate all the noise, that doesn't work. Ground absorption does work at really long distances. Low humidity works. We talked about wind and temperature. And I'm to the end of my presentation. Matt, do you have anything to add to this?
No, I think you did a pretty good job. I think at some point in the future, I would like to do an additional presentation on what our mechanical team can do to quickly kind of determine whether they need additional acoustics help. Whether it's things like being able to quickly go through a single line system from the air handler down to a room and kind of find all the different parts and see if you might have problems. But this is a great overview on generally how everything works and what kind of things we need to know. The most important things I would take out of this one are, like I said before, is how to describe the sound that you're hearing in a problem, and really the correct information that we need if we're trying to help design or determine an acoustical problem. Being sound power, if that's the reference, or sound pressure level, and the distance for sound pressure level. So those would be the two things I would absolutely take away from this, but it's all good stuff.
Okay, thanks, Matt. And I'm really in support of coming up with some rules of thumb, especially for our HVAC people, to say, is this thumbs up? Is this, I need to talk to acoustics? Or is this, oh, I'm screwed?
Exactly. And I think there's some points where the easiest thing that everyone goes to is, do we need a silencer? But it really depends on where in the system it is, because acoustics is an entire system. And there's some times where your air handler, where everyone puts their silencers at, is not the controlling noise. Where if you get to the end of a system, if you got your terminal box, that terminal box might be louder than your air handler unit at that point. So adding a silencer upstream doesn't do anything. So it's these little things where there's no prescriptive method. You can't just say put a silencer in, you'll be okay. There's a lot of different components that make noise. So that's something that we'd like to get everybody a little more comfortable with, knowing where in their system they might have to look at.
Matt, and I'm assuming Taryn will cut all this out at the end of the conversation, but
Sure.
uh, part two of this seminar discusses more building acoustics, and I'd love some input from you and David about that because, like, I think I go into an issue where we bought like the world's best high school audio scoreboard system, and the high school gymnasium was built with wood floors, painted concrete block walls, and a metal deck ceiling, not an acoustical metal deck ceiling, a metal deck ceiling. And they said, well, we can't understand anything the scorekeeper says. And I said, it's because your building is part of our system.
Mm.
And, they had to put some acoustical panels on the walls and then it all went away. It's like, I really want to get it across to our architectural clients that we can help them with that sort of thing. And their building is part of our system. It's not just like buying the best amplifier in the world.
Oh, yeah, absolutely. Our mantra is always acoustics and AV go hand in hand together. You can't, exactly what you said. You can't have a great AV system and terrible acoustics and expect it to work. But you also can't have a perfect room but nothing to excite it. So
Okay. So, that's all I've got. And there's part two, which Matt and David, I'd like you to be in on in January because I want the business to come to you guys, not me.
that sounds good to me.